Now that you've got some experience thinking about stacks and queues as data structures, let's take some time to think about implementation details for the queue in particular. So if a queue uses an array to store its data, meaning that the first location that's available is index 0, and then the last locations might have some empty space there, as I've shown in the first diagram off on the left here. Which end should it add to, meaning the back of the queue, where things get added at the back of the queue, and which end should it remove from, referred to as the front of the queue, where patrons get served or data gets offloaded from a buffer. Because what you might have caught on to when talking about the stack was that it only has one location that it needs to add to or remove from. It adds to the same place that it removes from, the top. And so we can easily make the top be these empty spaces out here. We'll call them the end of the array, where the last real data is. It can add just past that last real data. So if I'm asked to add 2 to this stack, that's no problem. I use an empty space. As long as I have space remaining, I can just add things to it. If I'm asked to add 1, also no problem. I can just put it in that spot. If I'm asked to pop, if I'm asked to remove, then I could just remove from there, and that space now becomes available. I could mark it empty, or I could just treat it as it's empty from there onward. And if I'm asked to add more in that space, well, that's great. I just put a new value in that location there. So the stack only needs one place, and we've seen where the easy place is to do both of its operations from. A queue is going to need 2 places, a front and a back. And so what I want you to do is to pause, take a moment, and think about this question. Which end of the array should we add to, and which end of the array should we remove from when building a queue? Pause and think about it. You may have realized that if we're using a standard array where the starting index is 0 and it's got some limited space and might have empty spaces out toward the end, then we really only have 2 possible choices. So we have the choice to add at the end the empty spaces and remove from the front the location 0, or we have the option to add at the front location 0 and to remove from the end, that place where there are some empty spaces just after. So we could add at the end, remove from the front, start, we'll call it start, index 0. And we could add at start, index 0, and remove from end. Let's take a look at the performance, how it would actually look to do either of those 2 things. So if we add at the end, we want to add the number 2. Hey, that looks great. That looks about like my stack. I was able to add stuff. I could add more, no problem. So adding at end, this looks good. Removing from the start, however, if I wanted to maintain that array behavior where index 0 is where my first real data lives, then I've got to move everybody over when I remove the 5 in this example to maintain the array and the consistency we expect from it. So that behavior is no good. If I want to do the opposite, then I right away can see where my challenge will come in, because adding at the start leads us to that other bad behavior that we sometimes see in arrays, where if I'm asked to add 2 here, I have to shift 3 over to make space for it, which means I have to shift 4 over to make space for that, and 5 over to make space for that. So I get bad behavior from adding at the start, but hey, removing would be pretty easy. I could remove the 5, and I could remove the 4, and so on. So removing looks good in that scheme. So with a standard array, we're running into trouble with the queue in one of the operations or the other, because a queue must add at the opposite location from where it removes. But what if we didn't limit ourselves to an array? What if instead we thought about a linked list where we had a head and a tail to it, which provide us with two automatic locations where we could either add or remove from? As long as that linked list has both next and previous pointers, you may recall that you get fast performance from adding at the head or adding at the tail, and you get fast performance at removing from the head or removing from the tail. So if we have a doubly linked list with a queue, if I wanted to add something at the head, that's no problem. I can just link it in right there at the head. Or if I wanted to remove at the head, that's also no problem. I just move the head pointer forward, and I'm now looking at, and I make a few other changes, and I'm now looking at having removed that item from there. Likewise, if I wanted to add at the tail, no big deal. I link it in with the tail, and I move the tail pointer. And if I want to remove from the tail, also no big deal. I can just change the tail pointer and a few other small things. So in the case of a linked list, a queue can use either. So either end works for either operation, as long as I add to the opposite place from where I remove. It gets a queue's behavior automatically. If I add at the head and remove from the tail, then I've created a back and a front to it, and vice versa. If I add at the tail and I remove from the head, then I've created again a back and a front and a back to my queue there. And if I do that consistently, it behaves as a queue. I get that first in, first out behavior from the implementation there automatically. I could get that first in, first out behavior from an array the same by simply adding it at the opposite location from where I remove. But we see that we get slow performance for one or the other of the operations, whichever one I have to do at the start, at index 0 in that array. So you'll look at some deeper details of implementation and examine a little more these choices for performance when implementing queues and stacks as you look at section F, G, and H of the activity.